Hey everyone, looking at class number 56 here. I'm not really going to write anything on this. I'm just going to talk you through it because a lot of this is either simple calculations or stuff that we've seen before. So the first was just kind of reviewing some kinematics questions that we saw all the way back in like the fall. So the first question was, we throw a ball up with the initial speed of 25 meters per second. How high does it go? So, standard, the initial 25 meters per second, we're looking for d. V final is 0 because at its highest point, its velocity is 0. Acceleration is negative 9.8 meters per second squared because gravity is slowing the object down as it goes up in the air. So we don't have time, but we can use the timeless equation. It's a classic. And working through, we get that the distance, the max height, is 31.9 meters. The other one is the opposite scenario where we drop an object from a certain height. So now we know the height, we know d. We know the initial velocity is 0 because we're dropping it. And we know the acceleration is positive 9.8 meters per second squared. We need to find v final. We can actually use the same equation here and get that v final is 28 meters per second. We'll come back to this in a little bit, and we'll see why we did this. So let's get into energy a little bit. So kinetic energy is energy due to something moving. So if something is moving, it has kinetic energy. Kinetic energy's equation is 1/2 times mass times velocity squared. Important note, only the velocity is squared. We measure all energy in this class in joules. What is a joule? It's a derived unit, kind of like a Newton is. It's a kilogram times a meter squared per second squared. We'll get into that more a little bit later, but you can kind of see with the units here how that ends up being. Mass is in kilograms, velocity is in meters per second, and it's squared, so it's meters per second times meters per second, meters squared per second squared. All right, but just remember it's in joules whenever you're looking for energy. Mass absolutely must be in kilograms. So to get the kinetic energy of this golf ball, you know its mass, you know its velocity. Just make sure you convert that mass to kilograms, so it's 0.046 kilograms. Okay, you got to move it 3 places. We get 88.4 joules. Now, if that golf ball were at rest, its velocity would be 0 meters per second. Therefore, its kinetic energy would be 0 meters per second. You really don't even need to do all this work. You know that if something is not moving, it has no kinetic energy. Now, potential energy is stored energy, if you will. And we're going to focus right now on gravitational potential energy, which is basically potential energy due to something's height. All right. If an object is really high off the ground, it can fall. It can gain kinetic energy. If it's on the ground, it can't fall. So it doesn't have potential energy. So our equation for potential energy is mgh. M is the mass, always in kilograms. H is the height above, basically the height above ground level. And it's always in meters. And little g is positive, always positive in this equation, 9.8 meters per second squared. So how does potential energy, or excuse me, how much potential energy does a 30.2 kilograms of bricks have on the third story of a building at that height? Well, mgh, there's our mass, there's little g, there's h. It has about 3,285 joules of energy. How much potential energy does it have at ground level? Well, at ground level, again, if the height is 0, no potential energy. You don't even have to do the calculation. So we know the total energy of a system is, so this is on your reference table. The total energy of a system is equal to its potential energy plus its kinetic energy plus this Q term, which is heat in the system. We frequently only talk about potential and kinetic energy. We frequently ignore friction, but there are friction questions that we do have to be aware of. So I like to throw it into equations, and then each time it's 0, or if there's no friction, you can write that that is 0. All right. So I just want to show you really quickly conservation of energy. It's not actually something we're going to do for a while, but I do think it's important to just talk about it now and why it can be so useful. So looking at the question from the beginning of class, we throw an object up in the air. We know its initial velocity, its initial height, its final velocity, but we're looking for its final height. So using those values, we can set up the conservation of energy equation. ETI equals ETF. This is really similar to the conservation of momentum. So just think about it like that. Potential energy initial plus kinetic energy initial plus Q initial equals potential energy final plus kinetic energy final plus Q final. Now Q is 0 because there's no friction in this question. If you look up at the original question, it mentions that there's no air resistance. Then we just plug everything in. MGHI plus 1/2 MVI squared, just plugging in for potential energy and kinetic energy. The same thing for the final potential and kinetic energies. Notice how there's a mass in every term now, so those masses can cancel out. Be careful though, because sometimes it won't always cancel out. Like if there's a Q value here, then it won't cancel out. So just be mindful of that. Then we just plug in G times H initial is 9.8 times 0, so that's 0. 1/2 initial velocity is 1/2 25 squared equals, and then we have 9.8 times the final height plus 1/2 times the final velocity squared, which is, of course, 0. Solve through, we get the final height is 31.9 meters. That was actually the final height we found doing it the other method. But you can see the similarities. Hopefully you see the squareds and the 9.8s. So you can kind of see, and if you'd like to, we can talk about why they are actually sort of the same equation. This one and the one we used earlier. But it just goes to show you that all this stuff comes from the same basic principles. So now we're looking at the other one where an object is falling. So we know its initial height is 40, its final height is 0, its initial velocity is 0, its final velocity is what we're looking for. So we start off with the same 3 lines. These first 3 lines do not change. Okay, there's no friction and the masses still cancel. So g times initial height, 9.8 times 40, right? Because now it's dropped from 40. Its initial velocity is 0, so that's why I put a 0 in there, so that term goes away. Its final height is 0, so that term goes away. And its final velocities are unknown. Solving through, we get 28 meters per second, which is exactly what we got before. And there you have it.